You've seen it, right? A figure skater starts a spin, gliding gracefully, and then, bam, they pull their arms in, and suddenly they're a total blur. It honestly looks like magic, like they're somehow defying the laws of physics. But what if I told you they're not breaking the laws at all? They're actually mastering them.
So, that's the big question, isn't it? How in the world does a skater just speed up with no extra push, no visible effort? It feels like it should be impossible. But the answer is hiding in plain sight, tucked away in one of the most beautiful and fundamental principles of the entire universe.
Okay, so let's put on our detective hats. We're going to treat this like a real investigation and unpack this puzzle piece by piece. And the very first thing you need to know is that the world of spinning, well, it plays by its own very special set of rules. All right, let's dive right in. In our everyday world, when we're pushing things in a straight line, let's call it the linear world, the only thing that really fights back is an object's mass. A heavy block is harder to push than a light one. Simple. But in the rotational world, things get way more interesting. It's not just about how much mass something has, it's about where that mass is located. And trust me, that one little detail changes absolutely everything. So now that we know where to look, we can finally identify the prime suspect in our mystery. It's a concept that I absolutely love to think of as an object's rotational laziness. Now, the official physics term is moment of inertia, but rotational laziness just nails it, doesn't it? An object with a high moment of inertia is super lazy. It's really difficult to get it spinning, and once it's going, it's difficult to stop. An object with a low moment of inertia is the opposite. It's eager and easy to spin. And this one idea, you guys, this is the key that unlocks the entire puzzle. And the relationship is actually pretty simple. Look at the formula. Inertia equals mass times the radius squared. That squared part, oh, that is a total game changer. It means the distance of the mass from the center of the spin has this huge outsized impact. So when a skater's arms are stretched out, the radius is large, and their rotational laziness is through the roof. But the second they pull their arms in, that radius gets tiny, and their laziness just plummets. To really see this in action, just imagine a race between a solid sphere and a hollow ring down a ramp. Now, they can have the exact same mass, but the sphere will win every single time. But why? Well, because the hollow ring has all its mass way out on the edge, which gives it a really high rotational laziness. The solid sphere, though, keeps its mass packed in tight and close to the center, making it way less lazy and much, much easier to get rolling. All right, we've gathered all the clues. We understand the difference between linear motion and rotational motion, and we've met our key player, rotational laziness, also known as the moment of inertia. So, are you ready? It is time for the big reveal. You know how in our everyday world, energy can't be created or destroyed? It's just a fundamental rule? Well, the world of rotation has its own supreme, unbreakable law. It governs every single spinning object, from a child's toy top all the way to a spiraling galaxy. This law is called the conservation of angular momentum. Think of it like a cosmic balancing act. The total amount of spin in a system has to remain constant. Physics just demands it. So if one part of the equation goes down, another part absolutely must go up to keep everything balanced. So here it is. This is the moment it all clicks together. When the skater pulls their arms in, they massively decrease their rotational laziness. But the universe says, whoa, wait a second, your total amount of spin has to stay the same. So to pay back that debt, to keep the cosmic scales in balance, the only thing that can happen is for the skater's spin speed to shoot up. It's not magic, it's physics literally forcing them to go faster. And this is where it gets truly mind-blowing. This isn't just a neat trick for figure skating. You've just learned a fundamental secret of how the entire universe works. And what's so brilliant is that this single physical law is in action everywhere. The same rule that makes a figure skater accelerate also explains why planets move faster when they're closer to the sun in their orbit, and why giant clouds of gas spin faster as they collapse to form stars and galaxies. It's at work in the spin of a tiny electron, and even in the helical structure of our own DNA. It is everywhere. So the next time you see a skater pull their arms in and transform into a blur, you'll know the secret. You'll see them manipulating, simply and beautifully, a law that is woven into the very fabric of our cosmos. It makes you wonder, doesn't it? This principle is all around us. What will you see